Welcome to Study Loop.
Okay, so we have 1-bromo-3 ethylcyclohexane. I'm just going to draw this top down first, and we know that it's cis, which means the bromine and the ethyl are on the same side of the double bond, right? So if we call this carbon 1 and put our bromine there, then we can go in either direction. Let's go 1, 2, 3, and we'll put our ethyl here, and we know it's a wedge to an ethyl because it's cis. Okay, now we need to draw this in the chair conformation. I like to draw two parallel lines, two more parallel lines, and then connect them. All right, so let's call this carbon 1, let's call this carbon 2, and this central one carbon 3. And let's just start adding substituents. We know we're going to have an axial and equatorial substituent here. We can arbitrarily put bromine up here for now, and then that would make this hydrogen. And then when we look at carbon 3, we've got, once again, we have to add two substituents. So we'll do one axial, one equatorial. Now we have to decide which should be hydrogen, which should be ethyl. Well, we know that ethyl needs to be on the same side of the ring as bromine. So that means if bromine is up, then ethyl also has to be up. Right? So this would be cis. Great. So that's one chair conformation. The other chair conformation, I like to draw the two lines like that. And then I always number the one that's down to the right as carbon 1. So that means that this is going to be the carbon with bromine on it. And then we know we're going to have an equatorial substituent and an axial down substituent. Okay. If we keep the same relationship between bromine and hydrogen that we had here, bromine should be the upper of the two. And then we go 2, 3, down to ethyl. Okay, so now we're going to have axial down and equatorial up. And we know that between the two, ethyl should be the more upward of the two. So we'll have hydrogen axial down. Now we determine which is the more stable conformation. So is it better to have ethyl and bromine axial or ethyl and bromine equatorial, right? Because in the lower case, they're both equatorial. Well, anytime you have substituents, it's preferable that they be equatorial. That's just more stable. And the reason for that is that anything that's axial, like if we draw in this hydrogen here, there's steric interactions between the axial substituents, 1,3 diaxial substituents, or flag interactions, as they're sometimes called. So with ethyl or any large alkyl group, it's much more stable when it's equatorial, because when it's axial, remember that this ethyl is much bigger than a proton. It's going to be in the way, and the sterics are going to make this very unfavorable as the ethyl, the hydrogen, and the bromine interact with each other. So the more stable of the two conformations is the one shown here.